Now it goes. So now today is our last day of actual material. We're going to talk about the mean field dynamo. So I talked just before Thanksgiving about the dynamo, so I'll recap some of that. But I'm not going to go over it in crazy detail. But the basic idea, actually, I don't think I need you up anymore. Hopefully that didn't break anything. So let's talk about the sun. So we're going to kind of consider the sun for now, because this works pretty well for the sun. It breaks down when you try to do the galaxy for reasons that I'm trying to get paid to figure out. I have a grant at the NSF to try to figure out why the magnetic field in the galaxy is the way it is. So that's open research. But the sun we probably understand pretty well. We can see it. We got a lot of data on it. So, but it's still a complicated thing. So where does the magnetic field come from in the sun? Magnetic field. So if you write down the induction equation, d by dt of B is del cross B plus lambda del squared B. So we have the amplification term and the diffusion term. Remember, this is del squared of my quantity, so this is going to be a diffusion. This spreads things out. This term can amplify things. So I'm going to expand this thing with my favorite vector identity. So this triple product turns into B div V, V div B, B dot grad V, V dot grad B, V dot grad B, and this one is a plus, this one is a minus, but it goes away because we're going to assume it's incompressible. The sun is really incompressible. It's really hard to squish the sun. It's already as squished as it can get. Div B is 0 because of Maxwell's equations, and then we're left with V dot grad V, and that one gets a plus, and a minus V dot grad B. And then the lambda term. So let's talk about these two terms. So V dot grad B, this is the other half of the material derivative, the convective derivative, the full derivative. So if I push this over here, then I'm left with partial B with respect to time plus V dot grad B. This is just the Lagrangian derivative. dV dt. So this is the derivative that flows along with the fluid as it moves around. And this equals B dot grad V plus the diffusion term, lambda del squared B. Let's leave that on for now. This B dot grad V, we talked about this when we were talking about turbulence. This is stretching of the magnetic field. Why is it stretching of the magnetic field? Well, this is the gradient along the magnetic field. We've dotted B into the gradient operator. So this is the gradient along the magnetic field of the velocity. So you take your magnetic field and you pick 2 points. If those points are moving away from each other, then the magnetic field is going to get stronger because B dot grad B is going to be positive. So if you stretch the magnetic field, it gets bigger. Does that make sense? Now, the sun is differentially rotating. So it's rotating at the equator faster than it is at the pole. So I have 2 components that I'm going to talk about. We'll talk about the poloidal and the toroidal. I don't actually know if there are 2 R's in this word. I'm going to leave it there. So the toroidal field is like a torus. It's the azimuthal direction. And the poloidal field goes down from the poles and is the one that goes like this. Here's my sun. It's the one that comes out like this. me do that better. I can do that better. So it looks like that. It follows the lines of meridian. And in the sun, if you have a poloidal magnetic field, and then you have the differential rotation, then this part's traveling faster than this part, and this will get stretched out. And you'll get field line amplification. Now, if you just let this go forever, you will only have field in the azimuthal direction, because it will just wind up and there will be nothing left in the vertical direction. But that's not the whole story. So you also have buoyancy. So you have all these sunspots that pop up, right? So what happens when something is buoyant? When you have something that's buoyant, why do hurricanes form? What are the two pieces of physics that make a hurricane? Coriolis force and
Pressure?
the pressure's in there, but what's making the pressure do anything is the heat from the ocean. So you got this hot ocean, which heats the air, which then rises, which then leaves a hole, which then something has to come in to fill that hole, and that stuff will rotate like crazy because of Coriolis. So you've got this combined force of the buoyancy. Because it's buoyant, it then expands, and because it expands, it rotates. So the expansion and the rotation are related by the Coriolis force. The sun does this too. So if you have a magnetic field like this, then you have a plume that rises up, a plume of stuff, so some buoyant convecting blob of goo goes up. It's going to start to rotate as well. So then we'll have something that looks like that. So then I can rotate the toroidal field that we made back into poloidal field. So differential rotation plus the poloidal field gives a toroidal field. And toroidal field plus Coriolis gives me a poloidal field. So I have this back and forth between, and it's really a continuous process, but I have this kind of continuous process of twisting the field this way and then stretching it along this way and then twisting it this way and stretching along this way. And by this way we get a coherent field. Yeah.
Could you explain again how poloidal and differential rotation gives us toroidal?
Yeah. I think it all was on this board. I think everything that I wanted to say was right there. You got this star, and it's rotating faster here than it is here. So if I just paint a line on the surface, then this part's going to get pulled faster than this part. So it's going to get stretched into a toroidal field. Not quite like this because it's not just rotating on the axis, so I'm being a little bit exaggerated, but it stretches the field that goes like this into a field that goes like that. But you'll notice that I've got field going in this direction and field going in this direction. So just the differential rotation doesn't make the field any stronger, because everywhere you've got a little bit of that way, you've got a little bit of the other way too. So that doesn't net make the field stronger. You've got to flip this one around and make it go that direction. And then you've got a stronger field. So by flipping this one around, so differential rotation makes poloidal into toroidal. Did that make sense? Did that answer your question?
Yeah.
Okay. And then here's another word I spell wrong 100% of the time. Is it that way or are the vowels the other way? This language is dumb.
I think that's right.
Buoyancy plus Coriolis turns poloidal into toroidal and actually amplifies. actually adds magnetic energy. This one doesn't add any net magnetic energy. So that's how the sun works, kind of in cartoon. And these ideas are all due to Parker. This is Parker's model. Oh man, Parker's not here. So that's right, Eugene Parker. So that's the sun. So let's try to put some actual math to that. Is there anything else that I wanted to cover real quick? The other thing that I talked about, but I'm just going to give you a real quick tour of. So if you try to make an axisymmetric time stationary dynamo. So, okay, one of the things that we always like to do, we like to throw out as many derivatives as possible. The more derivatives there are, the harder the equation is. So if we want to throw out the radial, the theta derivatives and the time derivatives, you can't have a dynamo. This is Cowling. So Cowling has several anti-dynamo theorems that say when you can't have a dynamo. So this bit is a little tricky. The math is a little hairier than the math that we've done before. This is probably the hairiest math. I don't know, maybe. Because the dynamo amplifying a magnetic field from the magnetic field is a fundamentally three-dimensional, fundamentally time-dependent process. So there's no way around those two things. You can make it kind of axisymmetric, but it can't be time stationary. But we're not going to make it axisymmetric. We're just going to throw out some derivatives. So Cowling says no dynamo in certain situations. So let's go put some math on this. So what we're going to go through today. So basically, the reason that I'm going through this, even though like I'm doing hairy math on the last day of class, because this pulls together everything that we've done so far in the semester. So all of the stuff that we've done, all of the linearization and perturbation and throwing out small stuff and Fourier analysis and MHD, all of that comes together here, and we can describe a model of sunspots. So that's all pretty fun. So this really is retreading on ground that we've already gone over a bunch, and also fun and exciting stuff. So, okay. So we're going to say that, do I need, no, I don't need any. He does some business with the, with the current that I'm going to skip because I don't care about it. I forgot to grab chalk. I only have this tiny chalk. So we're going to do the same stunt that we've said before. B is equal to B bar plus B prime. And V is equal to V bar plus V prime. So let's stick this into the induction equation. dB dt equals del cross V cross B plus lambda del squared B. So I plug this into here, and I'm left with d of B bar plus d by dt of B bar plus d by dt of B prime equals del cross V bar cross B bar plus V prime cross B bar plus V bar cross B prime plus V prime cross B prime. Of all those terms, I got 4 terms that I should have. One of each flavor, yeah. Plus lambda del squared B bar plus B prime. I'm going to hang on to this for a second. That's a lie. I'm going to screw up and erase it and be mad when I erase it. But
It's still lambda Del squared on the B prime as well.
Yes. So if I average this, I draw this line there and try to not erase the stuff above it because I need that stuff in a second. So if I average this term, this equation, remember that if I have q bar plus q prime, then I average this, and that's just equal to q bar, because the average of q prime is 0 by construction. All the fluctuations all average out, because that's how we designed it. So if I average this, then I get an equation for the evolution of the mean magnetic field. d by dt of v bar is equal to del cross, who survives? This guy survives because the average has already been done. So this is v bar cross v bar. So the average of this term is itself. Plus this one. So this one, the average of this term is going to be 0, because the average of the fluctuating term is 0, and the average of b bar is b bar, so it doesn't depend on the average. So this one goes away, and this one goes away. And then I'm left with this term, v prime cross b prime, bar over both of those things. Now this is different. Now I have an extra term that wasn't in the induction equation before, plus lambda del squared b bar. This one goes away too. So now, just like the Reynolds stress, so we did this with the Navier-Stokes equation, and we got a term that looked like this, except it was vi vj instead of v cross b, but same idea. We've got the average of the product of the fluctuating terms. What this represents is small scale velocities twisting up small scale magnetic field to make larger scale magnetic field. That's what this equation is saying. So I've got small scale velocity and small scale magnetic field. They interact with each other to create the large scale magnetic field. And we call this the electromotive force, is v prime cross b prime average. I'm actually going to write this up here. E is v prime cross b prime bar, average of that. Does that make sense? So this is kind of the same thing that we've done already. Now what we want to do
The
is
last term there is just supposed to be lambda Laplace squared.
what's that?
The last term here you have lambda. Is that supposed to be b bar?
Yeah, that's b bar. Because it's just like this term, and when I average this, that one goes away, and this is the one that we're left with.
Is b bar not supposed to be like the non-fluctuating part?
Yeah, it's the average part.
Since that will be stationary, right? I mean,
Oh, it doesn't have to be. It doesn't have to be stationary in time. So these are ensemble averages. So it's better to think about this as kind of an average over time, but kind of not, and kind of an average over space, but kind of not. So it's really an ensemble average over many realizations of the same thing. So it doesn't go away for smoothness concerns. Does that help?
I was actually expecting that to be like b prime, not b bar.
Yeah. So so the term looks like lambda del squared b bar plus b prime, and then I average the whole thing. So I take an average of this whole equation to get this one, and then when I take that average, that's equal to lambda del squared. The del squared doesn't care. I got b bar bar, which is just b bar. So the average of the average is itself, plus lambda del squared b prime bar, but b prime bar is 0, so that term goes away. Does that make sense? Yeah. Yeah, thanks for asking. I super appreciate it, because I don't know how fast I'm going. Okay, so we have this electromotive force, and we need to track it down. So what we want to do, the electromotive force is a function of correlations that I don't understand. Why correlations? So if v and b prime are uncorrelated, then for every V up, B up, I have a V down, B down. And so this, if V and B are actually uncorrelated, then this average is actually 0. So I need to have some correlation between the velocity and the magnetic field to amplify the magnetic field, which makes sense, yeah.
Can you repeat that?
Yeah. So, yeah, I don't care about it yet. Yeah, so E is V prime cross B prime bar. So, and I haven't really said what correlated actually means, but if V and B prime are both random fluctuations that don't care about each other, then when I add them all up, I'm going to get 0. Because every time this one goes up, this one goes down, or the other way around, and sometimes the other way, because they're uncorrelated and random. So the product of two random things that are signed quantities, if you average them, if they're uncorrelated with each other, then this average is 0. And you can have that. It's possible. But it's really probably likely that the magnetic field and the velocity are in fact correlated, because if you think about some large-scale magnetic field and some velocity that's keeping this magnetic field afloat, and then little fluctuations, little velocity, so this is V prime, these little fluctuations are going to make little distortions in my magnetic field, and these are all B prime. So there's going to be a relationship between the velocity and the magnetic perturbations that are going to help us out. But there has to be some order. There has to be some order in the flow. Otherwise, if it's totally random, then you get nothing. That's really what it comes down to. So we want to write an expression for E that depends on things that we can measure. We can measure the mean flow. We can measure the mean magnetic field, though I can tell you that measuring magnetic fields is a pain in the ass. But let's pretend that we can do it pretty accurately. So we know the mean velocity, we know the mean magnetic field, and we know the statistics and averages of the fluctuating velocity. So we want to write, because these are the things that we can measure pretty easily. I can measure the velocity of the sun, the large-scale velocity of the sun. I can't measure the little fluctuations. It's little and far away, but I can measure the large-scale velocity. I can measure the large-scale magnetic field, and I can measure the average of the fluctuating magnetic field. I can probably measure some of the fluctuating field, but I can't measure all of it, and then I can't save all of that data. The sun's huge. It has lots of points, so I can't save all of the fluctuating information. So I need to be able to write an expression for the electromotive force that depends on statistics of the fluctuations. So that's where we're going to go. So we're going to get something like that, and we're going to get a simpler equation for this that doesn't have this nasty term in it. So this nasty term has things that I don't understand. We're going to simplify it to get something that doesn't really look any better, but has things that we can get our hands on. And then we'll drop in some Fourier analysis and show that this makes waves that travel inwards. So you can reproduce this butterfly diagram pretty simply. After a couple boards worth of algebra. So, where am I at? Okay, so what we want, so the goal we're after is this guy. V prime, we're assuming Jesus gives us V prime, and this is something that is fixed and coming at us, and we know the statistics, but we don't need to write down an evolution. So the velocity is set by something like the dynamics of the galaxy, or the nuclear burning at the center of the sun, or the giant motors that are spinning around your liquid plasma dynamo. So you can do this with a giant. I told you guys about liquid sodium dynamos. Did I mention those before? No. So you can do this in a lab, but it's really hard. So what they do is they get a huge tank of gallium or liquid sodium, and they spin the crap out of it, and they amplify magnetic fields with these huge tanks. The problem is liquid sodium is super explosive. So they only do that way out in the desert. So anyway, where am I at? So the fluctuations and the velocity come from the turbulence and the magnetic fluctuations. Let's see if we can get a handle on that, because this is something that we're not ever going to be able to measure, v prime, and also it's an output of what the velocity is doing. So let's get an equation for b prime real quick. So db prime dt is equal to db dt minus db bar dt. So I just take this equation and subtract the average equation that I erased. And I'm left with, well, basically this, but some of the other stuff goes away. So when I subtract off the mean equation, what did I have in the mean equation? I had a v bar cross b bar, and I had an electromotive force. In this equation, I have a v bar cross b bar. Again, I have no electromotive force. I have this, but I haven't averaged it. So the fluctuating b prime evolution is equal to del cross v prime cross b bar plus v bar cross b prime plus v prime cross b prime minus the electromotive force plus lambda del squared v prime. So this is an equation for the evolution of the fluctuating magnetic field. And I've got a term that looks like fluctuating velocity interacting with the mean flow, or with the mean field. I've got the mean field interacting with the fluctuating field. I got the fluctuating field interacting with the fluctuating field. And I've got the electromotive force, which is actually working on the mean B. And then I've got my diffusion, which is still going to happen. So now, so the next assumption, so now we're going to make an assumption. I haven't made any assumptions yet. So this is accurate. This is a true statement. Now I'm going to make an assumption. We're going to assume that the fluctuating magnetic field is small. How small? Smaller than everything else. So that lets us kill this term and this term. Oh, and this term, which has got a fluctuating B in it too. Is that everything that I did?
What about the del squared term?
We're gonna, yeah, let's throw that out for a second. That's just because, so here we're just gonna throw this out because we want to play with these other terms. Oh no, I'm sorry, it's gotta be prime too, yes. That one goes away for the same reason. Derp. One of my better days. So then we're left with d by dt of b prime is del cross b prime cross b bar. So basically now we're saying that the fluctuating magnetic fields are only coming from the fluctuating velocity interacting with the mean field. And that other fluctuating magnetic fields might be produced, but they'll be so small that it doesn't matter. Now we'll use my favorite vector identity and rewrite this. So let's rewrite this instead. Now we're going to pull a physicist stunt, and we're going to turn this time derivative into just a time. So dB dt turns into b over t. So now b prime equals tau times, I'm going to use my favorite vector identity on this guy. v prime dot grad b bar minus v bar dot grad b prime, v bar dot grad b prime. This gets ugly. I need all these things, so I want to make sure this board's second. Okay, so now I have an expression for B prime. It's got this tau. This is the correlation time scale. I just made up a time. I just invented a time, so there's some time scale. This is the correlation time for V and B. So over some kind of time scale, they're correlated. We have hands. Time scale. So some time scale for the system to evolve. We've got B prime. So now we can drop that into my expression for the electromotive force. Because that's really what we're going after, is an expression for the electromotive force that only depends on things that I can measure pretty easily. So V prime cross B prime. We'll take an average of this in a second. Okay, this is equal to epsilon I j k V prime j B prime k. Or k. Is there a bigger one? A little bigger. We'll change colors. So this is just the definition and how epsilon I j k works. Stop me if you want me to talk about epsilon I j k. We'll just take what we got for B prime and put it in here, and we're left with epsilon I j k. Normally I try to not look at my notes too much, because if I'm looking at my notes, then I'm not looking at what I'm doing. But here I'm going to screw it up if I don't. Vj prime. What does it look like? I got a V dot grad B, so I'm going to have a V and a B derivative, and a B dot grad V, I'm going to have a B and a V derivative. So I'll have two more terms. So the first term, this Vj comes from the cross product, and then I've got a Vk, and the first term is going to be, let's just write it out. This is going to be Vijkl dot d by dxl of B k bar times tau. This is the first term from over there, minus tau times VL times, what's the other term? VK dB K dxl. Did I do it right? No, I have too many V's. Why do I have so many V's? Yeah. K is the last index. The last index of that is B, so BK, V dot V. So the V is being dotted into the derivative, so these guys share an index. The B is the thing that carries the vectorness, so that gets the last index. So we're left with this expression. I have no insight on this expression. It's kind of awful. Let's keep simplifying, or making it harder, and then it will simplify in a second. So let's expand this out. So let's think about what we've got for a second. I've got one term that has a derivative of the magnetic field. Oh no, I wrote this wrong.
The second term you should call the B.
Yeah. It's harder to do algebra when you're this close to the board, because I can't see this term when I'm trying to look at this term. Also, I wrote it backwards in my notes than what I was doing here. BL dV K prime dxl. Okay, the indices were right. I just had B and V switched. So I've got something that's got a derivative of B and one that goes linear with B. So, okay, let's just say epsilon, my electromotive force is going to go like alpha ij, where I'll tell you what alpha is in a second, times Vj bar, plus beta ijk times dB bar j k dx j. Is that right? Yeah, that's right. And alpha is what? Alpha's got to be, alpha goes with the linear one, so that's this. So it's going to be epsilon I j k vj prime. Tau goes out in front. dvk prime dxl. So alpha is the relationship between velocity and its derivative. And beta ijk is equal to the other term, and it's equal to epsilon ijk vj prime. This one was that term, and that one is going to be this term. Tau in front, vl prime. Did I do that right? Oh, I didn't write it down here. But that's so the actual form of this. This is still horrible. This isn't useful. This is sorry, ij, alpha ij. I got another alpha that makes more sense that I like better. Okay, these is still horrible math. And it involves interactions that I can't really measure, and they're all kind of awful, and it's all three-dimensional. So let's simplify again. So we'll make another assumption. Assume it's isotropic. So this takes, let's see, you got to stare at this for a little bit for it to make sense. So I don't know if I'm going to, we're going to say that alpha equals -1/3 v prime dot del cross v prime. So this cross product simplifies to this, and we're going to have another term we'll call lambda t that's equal to 1/3 b prime dot b prime, and we also have a tau in front. And then my EMF becomes much simpler, and then I've just got alpha b bar plus plus beta dB dx bar. And alpha and beta now are only statistics of the velocity field that I can get my head around. Yeah.
Can you explain why it being isotropic lets you do that?
Lets me do this? Yeah, because this has all of the possible degrees of freedom that you could have. So I can't simplify this any further. But once I'm allowed to say that that rotating this is invariant, then it becomes this. I don't have a better answer than that today. Because I got distracted when I was at that part of preparing my notes. I was like, oh crap, I'm not going to understand that part well enough. So it simplifies to this. Why? I have an explanation, but I don't have a good explanation. But you can see that it's going to. Epsilon ijk is a cross product, right? And I've got vj and dv and a derivative of v. So this turns into v dot curl of v if you stare at the indices long enough. And this one similarly is just a sum on vj and vl, and if we assume that everything is isotropic, then you can throw a bunch of things out and all you're left with is the longitudinal term. So this is just the mean velocity. The important bit is this is the mean velocity. It's just v squared. And that's a simple thing to measure. And this one is v cross omega. And v cross omega is a special thing called the helicity. So this is how much spirally kinds of motion are in the flow. So the spirally kinds of motion are necessary for these dynamo things. You've got to break the symmetry. So you need spiraling motion, which is v dot omega gets you spiraling motion. So you need spiraling motion and some mean energy to make a magnetic field. How am I doing? Does that make sense so far? So my EMF went from the average of V prime cross B prime, which I can't measure, to be the average of alpha, which is something that I can measure, or in principle can measure, times the mean field, which I can measure, times beta, which is just the mean energy, which I can certainly measure, times the derivatives of the field, which I can in principle measure the derivatives of the mean field as well. So now, the last thing I'm going to do is actually use this and linearize it. Because I got 15 minutes left, so I can do that. So, let's leave this board and that board. Someday, I will have my stuff together enough to have all the boards that I need stuff on up in front, but I didn't do that. Fast and slow waves. Okay, so we're gonna do a couple things. So let's take a cartoon. Sorry, collecting my thoughts. So we're gonna make a cartoon of the sun. This is an egg-shaped sun. Let's make a round sun. That sun isn't gonna last very long. Round. There you go. So, and we're not going to do this in rotating in cylindrical or spherical coordinates because that's a pain in the butt. So we'll do it in Cartesian coordinates because that's easier. And we're going to say that Z is towards the pole. Y is the toroidal direction, and that's along the equator. And X is coming out of the board. That is also part of the poloidal field. So the poloidal field is X and Z, and the toroidal field is Y. Now, this is maybe only good for a little tiny patch of the sun, but that's okay. So we're going to do something kind of obnoxious, and we're going to write the magnetic field as By is a function of X and Z in the Y hat direction. That's my that's my toroidal field. Plus del cross A of X and Z in the Y hat direction. And this is my poloidal field. Now, I didn't actually say anything here. Here I just said B equals B, but I wrote it in a really ugly, complicated way. So this second term, so the first term, this is just the B component, and we're going to assume, let's assume that that we're roughly symmetric in that axis so that we can throw out all the Y derivatives. Now, we've got all these fluctuating fields, so we're not actually axisymmetric. We're just throwing out all the bulk Y derivatives. But there's still little fluctuations that break the symmetry. So, okay, so we're going to assume this, which simplifies things a little, but not a ton. So the vector potential, not everybody has had E and M yet, and I don't think that you've seen the vector potential anywhere else. So we talked about potential flow where I can say V equals minus grad phi, and V is a vector, and phi is a scalar. So phi is easier to deal with, so whenever we can, we'll work with phi. This is how we did the two instabilities things. It's how you do a lot of engineering, fluid dynamics, is working with the potential field instead. Why? Because it's a scalar. There's only one thing you have to deal with. V is a vector, so you've got three things to deal with. But you have this relationship between the velocity and a potential. You have a similar relationship between the magnetic field and the vector potential A. A is the vector potential. And it is a useful tool, but it's not as nice as the vector phi because it's still a vector field. It's tricky to get because undoing this operation is hard. So really getting your head around what A means is kind of tricky. So just all you really need to know is that B equals del cross A. We'll come back to that in a second. But you'll learn all about vector potentials when you get into E&M. So we're breaking our poloidal field into the curl of a vector potential. Yeah.
About what you said a little earlier about writing V is the gradient of phi.
Yeah.
Do you have to check first to see if V is conservative before you do that?
Yeah, that's a really good point. So when I say V equals grad phi, I only get to do that when div V equals 0 and curl V equals 0. So you're totally right. This is only true when the flow has the right properties. The vector potential is always true. That's just what the vector potential is. That's a definition of the vector potential. So if I have a magnetic field, I have a vector potential that made that magnetic field. So it's analogous, but really very different. So I'm going to write my poloidal field as the curl of this vector potential, but A by itself is a scalar. Here, this is a vector, but A is a scalar again, because I'm exploiting the fact that we're going to be in 2 dimensions, because I'm only dealing with 2 dimensions. This is just the x and the z components of the magnetic field. So the y component of the magnetic field is this one. This is the x and the z components of the magnetic field. And we're getting it from this kind of goofy way, and I'll show you why we're doing it this way in a second, because we do actually get to get rid of a vector equation and turn it into a scalar equation. That's really where we're going with this. So I have this slightly complicated description of the magnetic field. I'm going to define this quantity G. This is the shear, and it's dvy dx. We're going to assume that V equals only Vy and only depends on x and is in the y hat direction. So my velocity is very simple. My velocity only has a y component and only has variations in the x direction. So that's the altitude in our sun. This is overly simplistic. It's what I can get done in 12 minutes. So these are some simplifications, but they're not general simplifications, but you can get to an answer. If you want to break this and you want to make it more general, you can do that with certain restrictions, and that's all plenty cool. There's textbooks on that. So we're going to use this simplified thing where we only have velocity in that direction. Now, when I write B here, I mean B, but I'm never going to write down the fluctuating components, because I don't care about the fluctuating components anymore. That's what I did that page of the whole board of algebra for, was to get rid of the fluctuating components and write them as things that are just statistics of the system, that don't have to do with what the fluctuating components are doing, only have to do with the average of the fluctuating components are doing. Well, okay, that's 0, but averages of things containing the fluctuating components. So here we're only talking about the mean field from everything out going forward. So there's fluctuating field, so there's a fluctuating velocity, and that's going to get us all the rest of the symmetry breaking that we need. So there is still a fluctuating velocity, but I'm not going to talk about it, except for the fact that I just spent the last 30 seconds talking about it. But it doesn't show up in any of the math. So G is the shear, so it's just dvy dx. So it's just, how much is the fluid shearing against itself. And I can rewrite my, so the induction equation, which I'm going to write down, dv dt equals del cross V cross B plus lambda del squared B, our induction equation. So from that, I can write down dvy dt equals what? G dvy dx bx. So this is coming from this cross product. This V cross B cross product. If you write down, so we're just looking at the y component of B. write down everything else with all our assumptions. The only thing that comes from that cross product is g, the shear, times bx, the x derivative, or the x component of the velocity. So, and that makes sense. This is what I was just saying. By is shear times bx. I've got some field like this. I've got some velocity that's going like this. The velocity stretches that out. So bx is giving me by by way of the shear. Minus alpha del squared a plus lambda t, should I put it on there, del squared by. So now for a minute we're going to throw out the other lambda, because so this is the induction equation, and we have our molecular lambda here. Our mean field equation, which I didn't write down, has a lambda t and a lambda in it, but we'll throw out the other lambda and just have the turbulent lambda. You can totally forget what I just said because you're not going to notice that it's missing. This is the turbulent diffusion, which comes from that. And we threw out the molecular diffusion kind of in the background because nobody cares about it because it's little for astrophysics. For lab physics, you can't do that, but for the sun, you can. So dB dt is this. So I've got my amplification. I've got my amplification from the fluctuation. This is the dynamo term now. And I've got my dissipation from the dynamo. Similarly, okay, so I've got dB dt equals del cross V cross B plus del cross, oh, I should have written this down, alpha B plus lambda t del squared. Oh, I can't get that one at all. B. So this is what our, I didn't write this down. I should have written this down. So our mean field induction equation is a little different. It's dB dt equals del cross V cross B, just like before. Now these are all the average quantities, plus del cross alpha B bar plus lambda t del squared B bar. So that's a little small, apologize. But it's got three terms. It's got a del cross V cross B, which is just like the regular induction equation. And also we now get this del cross alpha B. That's our amplification term from small scale fluctuations. And then we've got lambda plus lambda t. And lambda t is this guy here, and that's our diffusion from turbulence. And the other lambda is the diffusion from molecules. So this is the same thing. I just threw out the other lambda. So you notice that I got a curl on all of these. So I'm going to just drop in del cross A for B, because that's a thing I can do. And then I'm left with del cross dA dt, that's this term, equals del cross V cross B plus del cross alpha B plus del cross lambda t del squared A. Okay, this is also ugly, but it's just the induction equation, but I've dropped in del cross A for B, and now everybody's got a curl on it. So now I've got an equation that looks like the curl of d by dt of A equals, I'm going to screw it up. We work out what this curl is. You're just left with alpha b y. Oh, this curl goes away because of all of the geometries, because I've assumed the velocities in a particular direction, and this is only an A only depends on x and z. So this term, because of the symmetries of the thing, fall away. So I'm left with this term, which is alpha by, and this term, which is lambda t del squared A. Okay, I wrote the curl of an equation. Maybe that's not a thing I can do, but that's the thing I'm going to do. So now, since this is always true, now this is true. So, I mean, you take the curl of both sides and then set it equal to 0, and then everything on the inside has to be 0. So dA dt is alpha by plus lambda t del squared a. So now I've got two equations that are a little simpler. I got this equation and this equation, and we're going to make another assumption. We're going to assume that differential rotation wins. So because of that, we're going to scratch out this term. So differential rotation wins. So now I've got two equations that also only have two terms in them. So now I have something that I've gotten to where I can actually write an equation that evolves. So let's recap where we're at. So we did all of this stuff, and now I'm going to erase all of them. This is probably all stuff that I want to point to in about 2 minutes, but I'm going to erase it. So how did we start? So we said we've got this simplified geometry where we've only got velocity in one direction, and my magnetic field is in this other kind of parameterization. We massaged some stuff and we dropped in our mean field MHD, and we're left with dvy dt equals the shear times bx, remember that guy, so this is just twisting the field into the y direction, plus lambda t, the turbulent diffusion, del squared by. So now I've got the by component is dominated by creating it from twisting up the bx and diffusing it by turbulence. And the a component, dt of a, which represents bx and bz, is equal to alpha by plus lambda t del squared a. Okay. Now, I'm going to want that space. So we're going to assume the same Fourier stuff that we've assumed a bunch of times before. A equals a naught e to the, how are we doing this? Sigma t, a goes like a, so I know an exponential is probably going to be a good bet. Sigma t plus I k z. And it turns out you can ignore the other two wave vectors for now. So a is just going to go like an exponential, and b is going to go like the same exponential, a naught e to the sigma t plus I k z. So we drop this into these two equations, and oh man, now I'm eating into your time, but I'll finish it real fast. Now I'm skipping a bunch of algebra because yeah, so you drop these guys into these guys, do a little bit of algebra that's really not that painful. It's just add the two things, and you're left with sigma, this guy, is equal to boom, 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 minus lambda t k squared plus I minus 1, yeah, it has to be an I, square root of alpha g. It's plus or minus there. Which will simplify, we're going to rewrite this as minus lambda t squared plus k, oh, did I write this wrong? Oh, sorry, k, there's a k in there. K alpha g over 2, square root of that, plus I times k alpha g over 2. So we did a bunch of work, and now we're looking at what the exponents are going to do. We're going to assume that it's going to behave like a plane wave, once again, and it's got some exponential time dependence and some oscillating z dependence. So for a dynamo to work, the real part of sigma has got to be positive. And you work out that this dimensionless number called the dynamo number, which is equal to alpha g over k cubed lambda t squared, which if I solve this for alpha g and plug it into here, it starts to make more sense. And you realize that this has got to be bigger than 2 for this part to be positive. This is the real part of my time dependence to be positive. So for amplification, I need this to be larger than 2. This is the relationship between alpha. This is the turbulence stuff. This is the helicity in the flow, and G is the shear in the flow. So I need twisting motions and I need shearing motions for this dynamo to work. And those are modulated by the diffusivity. So if the diffusivity goes up, then it's harder to make a dynamo. And the wave number, harder to make a dynamo with bigger wave numbers. That's smaller structures. And now I'm out of time because now we're way over. So does anybody have any questions on any of that? That's just kind of culminating everything. I'm probably not going to ask you very many questions about it. I will figure out what I'm actually going to ask you about MHD and let you know.
Our final is on
Tuesday.
Tuesday.
Thursday.
I just wanted to make sure.
I don't know. Hang on a sec. Let me pull that up before you.
FSU. Yeah. On the FSU syllabus, it's Thursday, but on the syllabus, it's Tuesday.
On mine?
On yours.
On the first edition of mine, it was wrong.
Okay.
It's right on the website. I don't have any stupid internet.
Well, I just looked at FSU's final exam schedule and it should be Thursday.
Yeah, go with that. Whatever, if it's in a PDF that I wrote, it's probably wrong. That's pretty good rule of thumb, right?
It should be Thursday at 12:30.
Yeah.
Yeah, Thursday at 12:30 sounds right.
The time block.